Hi everybody, this is Miss McClellan here to go over IM2 Notes 2.2.1 with you. What do these shapes have in common? We're talking about dilations. So for our learning goals, we have two. We'll write them in first person. I will be able to, 1, describe the properties of dilated images. Those being congruent, corresponding angles. Congruent corresponding angles. Proportional side lengths for the corresponding sides. Proportional corresponding side lengths. A common center. And parallel corresponding sides. You will also be able to dilate figures on a coordinate plane given scale factors, but that won't be covered in this set. Okay, so the very first thing we're going to do is a rubber band activity. And let's watch a brief video on that. Now, unfortunately, if you're watching this video, you're probably not going to do the physical version of the rubber band activity, but it is fun, and I think it will make dilation stay with you for a long time, so I do encourage you to try it. Okay, now we're going to watch that video of the rubber band activity taking place. Whoa. So in this video, students are dilating the little star into the big star using a series of rubber bands. Right there, they have 2 rubber bands together. And in the first one, I'll show it again, they had 3. Now, if you're doing this in class, we would be doing this activity, which is super fun. But hopefully you can still get the point just by watching. The way that the student is doing it is they're putting the knot where the rubber bands meet along the lines of the original star, and as they stretch that, they create a dilation of the image. Okay, thanks for following along. Let's keep going with the lesson. And we're back. What you just saw was a video that created a simple picture, designated a point of dilation, prepared for dilation by getting the rubber bands going, put the writing utensil in, and perform that dilation. And then here are some examples of results. Let's continue on with the lesson. Problem 2-47. Stretching a figure like we did in the rubber band lab is a transformation called a dilation. That's a big vocabulary word. A dilation image has several things in common with the original figure, and we're going to investigate what those things are. To answer this question, we will create dilations that we can measure and compare. So part A, we're asked to imagine that a rubber band chain is being stretched from the origin, so from right here, so that the first knot traces the perimeter of the original polygon. And then dilate the polygon from the origin by imagining a chain of 2, 3, 4, or 5 rubber bands to form the image A prime, B prime, C prime, D prime. I will start with a chain of 2. Okay. So first rubber band hits A, and then the second rubber band goes, see the same over, 1, 2, 3, 4. 1, 2, 3, 4. 2. So there I would have A prime. And now I'm going to do 2 rubber bands again, so down to D. That same distance and direction. Here's D prime. Doubling the distance from the origin to C. Here's C prime. Doubling the distance from the origin to B. Here's B prime. And let me draw that dilation as carefully as I can. Oops. All right, it'll have to be good enough. Okay, and I'm also going to do it in another color so that we can have our comparisons. So this time I'll do 3 just to keep it simple. 3 will be in this color. Okay. First stretch, second stretch, third stretch. Did I do it right? Did I go over 4? I have 2. Very good. There's A prime prime. Just naming it a little bit differently. 2 primes to indicate that it's my second image. Here's B prime prime. Here's C prime prime. I remember I had an art class once where we did this exact thing. Anyway, here's D prime prime. And let me drop that image. Okay. So if you were at your table, each team member would pick a different number of quote unquote rubber bands to use, but I'm just going to do 2 for this example. Part B. Carefully trace our dilated polygon from diagram 1 on tracing paper and compare it to our teammates' polygons. Part B is why I did more than one dilation for you. So what I'm going to do is I'm going to compare the angle measures of each polygon by dragging my polygons on top of one another. All right, I noticed that these angle pairs are all the same. So those corresponding angles are congruent. Let me mark that with dark and obvious lines. So B double prime is congruent to B prime is congruent to B. A double prime is congruent to A prime is congruent to A. D double prime is congruent to D prime is congruent to D. And I'm going to fit 4 somehow. Okay. C double prime is congruent to C prime is congruent to C. Right. So what I've noticed is that the corresponding angles are congruent when I dilate. All right, let's compare the side lengths of each polygon and see how those might be related. That means I've got to find the side lengths, and frankly, I'm not willing to deal with the diagonals. You could do it with the Pythagorean theorem, but I'm going to do just the straight parts. 2, 4, 6, 8, 9. Got length 9 right here. 2, 4, 6, length 6 right here. For my polygon my double prime polygon, I've got length 2, 4, 6, 8, 10, 12. 13. Let me count again. 2, 4, 6, 8, 10, 13. That doesn't seem right. I have to double check that. Okay, let me see down here. 2, 4, 6, 8, 9. Okay, and I'm back and I miscounted this line for that I'm going to highlight for you right now so that you can make the correction. Okay. Please be careful and make sure the number you have written here says 8 and not 9. I apologize for my error. Let me just highlight all the other measures so that you can make sure you have those too, because I realize this has gotten a little bit messy. And this last length is in fact 12. 2, 4, 6, 8, 10, 12. All right, now we can continue. We're going to compare the side lengths. So I'm going to make, I guess, proportions. Like if I'm going from 6 to 9, is that the same as going from 8 to 12? Let's check with a fraction. Is 6 over 9, well, that's equal to 2/3. Okay. And then the other one was 8 and 12. So is 8 over 12 also 2/3? It is. So I noticed that they have proportional corresponding sides, meaning they have a common scale factor. The sides have a common scale factor. So they have proportional corresponding sides. Okay, part C. In this problem, we will dilate the triangle FGH by a factor of 3. That's like having 3 rubber bands, and using point D as the center of dilation. Here we go. Now I'm doing a factor of 3, so I know everything that I'm going to do will be multiplied by 3. So originally, to get to from point D to F, I went over 2 and up 2. I'm going to have to do that 3 times. So over 2 and up 2. There we go. A length of 3. Now to get from D to C, how far did I go? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'll have to do that 3 times. I've already done it once, so I'm going to do it 2 more times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I'm going to do it one more time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And there is my point for G prime. And let me label F prime as well. And now for H. Okay, so H is up 2 from D and then over 1, 2, 3, 4, 5, 6, 7, 8, 9, 9. So, and sorry, it's actually up 3. So up 3 over 9. All right, I'll go over 9 2 more times. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to do that one more time. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I'm going to go up 3 2 more times. 1, 2, 3, 1, 2, 3. A convenient way to find new points is to do all of the horizontal part at once and all of the vertical part at once. That's something that I got from studying, I think like intro to physics or something. Anyway, breaking the coordinate plane into horizontal and vertical parts. All right, now I'm going to draw as carefully as I can my dilated shape. So from F to H, I have a line, from H to G, and from G to F. There we go. I have F prime, H prime, and G prime. And we're asked, do our observations from part B still apply? Well, let's remind ourselves what those were. The corresponding angles were congruent, and there is a proportional relationship between the corresponding sides. All right, let's see about that. I will check the angles first by tracing the small shape and moving it on top of the big shape. Okay, angle F and F prime are the same. Angle H and H prime are the same. And angle G and G prime are the same. So the angles are still congruent. The corresponding angles are congruent. So far, yes, the corresponding angles are congruent. Furthermore, let's look at the side length ratios. Well, I don't want to use the Pythagorean theorem, which is what you would need to do in order to solve for all of these lengths. So I'm going to use components. For example, I know that corresponding parts should be congruent. That actually works for any part of a triangle. So I'm going to check, corresponding parts should be proportional. So I'm going to check if this line right here is proportional in each triangle. Let me see. This is approximately 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. It's about 8. And this is about 3. I'm just going to say that the corresponding sides are proportional. And sometimes it happens that you try to find an easier way to do something and it is not easier. And that's the case right now. So actually, I'm going to use the Pythagorean theorem because we're going to do this problem right. Meaning we're going to complete this problem. All right, so I've added some right triangles to my dilation and original figure. And now I'm going to find the length of that diagonal. Okay, so this triangle is a 3 by 1 by x, and this triangle is 3, 4, 5, 6, 7, 8, 9, 9 by 3 by x prime. Now I notice that from the little triangle to the big triangle, I'm multiplying the side lengths by 3. If that carries for x, then I'm going to say that the corresponding sides are proportional is satisfied. Okay, so to solve for x in this triangle, I have 3 squared plus 1 squared is x squared. That's 10 equals x squared. That's the square root of 10 equals x. So somehow this should turn out to be 3 times the square root of 10. We'll see. So this is 9 squared plus 3 squared equals x prime squared. That's 81 plus 9 equals x prime squared. That's 90 equals x prime squared. Okay, I'm going to take the square root of both sides. Woof. And that gets me square root of 90 equals x prime. And how can we check if the square root of 10 is 3 times the square root of 90? Well, I'm going to use a calculator. So the square root of 10, according to my calculator, is about 3.16. So 3.16 is about equal to x. And the square root of 90, according to my calculator, is about 9.49-ish. If I divide that by 3, that equals 3 times 3.16. Common scale factor, these corresponding sides are proportional. A delight. Let's continue. What conjectures can we make about dilating any polygon? Well, based on my experience in this activity, I conject that when a polygon is dilated, corresponding angles will be congruent, and the side corresponding side lengths will be proportional, meaning they will have a common scale factor. Period. We continue. Okay, this is the last problem before we sort of summarize our notes. This is 248, similar polygons. We use the word similar to describe two polygons that look alike but are different sizes. In particular, similar polygons can be mapped onto each other with a sequence of rigid transformations plus a dilation. So in the problems below, we're going to try to figure out which shape does not belong and then answer the follow-up question. So part A, circle the polygon which appears to be the exception. Well, I wonder. Let me trace A. Does A have all the same angles as C? It does. Does A have all the same angles as B? It does. Does it have all the same angles as D? No, it does not. Different angles. So D does not belong because it is not a dilation. Not all corresponding angles are congruent. All right, now let's do a sequence of transformations that would map one polygon onto another. So I'll move A to C. I'm going to move a vertex of A to match with a vertex of, what was it, C? Then dilate A to get bigger to match with C, to lay on top of C. And I'm actually going to do that. So I'll use blue, I guess. Doesn't really matter. Here's A. I'm going to move A so that one of its angles matches up with C. And then I actually can't dilate with the program I'm using, but I would dilate until this angle ended up here. This angle would become here. That angle would go here, and this angle would go here. And this would be my point of dilation. Okay, part B. Circle the polygon that appears to be the exception. Let's see. I think I can tell that it's G, but I'm still going to check the angles. Oh, this one's harder. I can't quite check the angles because there are reflections involved. You know what? I don't have the power to rotate with my computer, but I'm going to say that this angle in G is different than the corresponding angles in the other shapes. So I think G is the exception because its obtuse angle looks smaller than the obtuse angles in the other triangles. And what's the sequence of rigid transformations? Let's pick a hard one. I'm going to go F to H. So move the vertex of the obtuse angle in F to touch the obtuse angle in which one? H. Then reflect horizontally, keeping those angles touching. Next, rotate until the angles, the obtuse angles, match up. Then dilate until the shapes have the same size. And I should specify that the point of dilation is that obtuse angle. Okay, you didn't have to do the hardest version of this problem, but I thought it would be more fun because who doesn't want to rotate? Who doesn't want to reflect? Okay, 2.2.1, math notes, dilations. This is the last thing we're going to do. It's a summary of our learning. So today we learned about dilations, and a dilation is a transformation that preserves, that means keeps the same angle measures of a polygon, so the angles don't change, but multiplies all its side lengths by the same scale factor. In a dilation, a figure is stretched proportionally from a particular point, called the point of dilation, or center of dilation. So for example, in a diagram at the right, triangle ABC is dilated from point D to form the image triangle A prime, B prime, C prime. Here's our original ABC. Here's A prime, B prime, C prime. Notice that the dilation image has all the same angle measures as the original, and all of the sides are parallel. This is something that we did not observe during our notes, although some of you may have observed it. We didn't write it down, and it is a property of dilations. This is a property of dilation. Dilated figures produce parallel corresponding sides. Now, if the point of dilation D is located inside a polygon, such as in this case, right here, then one of the polygons will be inside the other one. If the point of dilation D is on a vertex of the original polygon, so for example, if we had this is our original polygon and this is our point of dilation in this quadrilateral DEFG, then the image of that vertex remains in the same location. And that makes sense because, for example, let's say this was times 3, 0 times anything equals 0. So the point of dilation has 0 movement from itself, no matter what the scale factor is. Okay, two sides will always overlap. The non-overlapping corresponding sides are parallel. The corresponding sides are also parallel, but it's trivial to say so. I mean, the overlapping sides are also parallel, but it's trivial to say so because, I mean, a line is parallel to itself, but it doesn't give you any extra information to say so. Okay, dilations either reduce or enlarge a figure. If a scale factor is less than 1, then the figure is reduced. And if a scale factor is greater than 1, then that figure is enlarged. This is the end of our notes. I hope you found them useful, and I'll see you next time. Bye.